This video is about double integral over general regions. In the previous section, we learned how to integrate double integral over a rectangular domain. And this one can be written as, this double integral can be calculated by integrate two single integrals. C to D, f x y dy dx, or C to D, a to b fxy dx dy. In the previous section, our domain here, think about this is x and y. Your domain here is a rectangle. X is from A to B, Y is from C to D. Okay, you can view this. Look at this one. The outside one is dx. X is from A to B. Inside Y from C to D. Now, look at this one. You can view, you project this region D R there on the x-axis. Find small, okay, you have so many points here. For all those x, find the smallest x coordinates, which is A, and the largest one is B. Okay, so basically anything in this strip, they have their points, x is between A and B. Obviously, this point is not in that region, so we have a restriction for y coordinates too. So, for the point to be inside this region R, your y must be what? Bigger than C, less than D, right? That's why we're C to D. Okay, for the second iterated integral, you sort of project this rectangle on the y-axis. So similarly, you find the smallest y-axis and the largest y-axis, y-coordinates. Okay. Then that means everything on this strip, they have their point with their y-coordinates between C and D. Okay. Now for any point to be in this region R, your x must be bigger than A and less than B. So we got our second iterated integral. Okay, in this section we're talking about general region. How about your domain is now rectangle? What do we do? For example, my domain is like this. Not a rectangle anymore. Now we do the same thing. This time we call it D, okay? R is sort of stand for rectangle. Okay. Now, this is region D. D is a general shape. For the region D, this double integral also can be written as a two iterated integral. Okay. So, for example, we want the dx go outside. So always first determine which one you want to go outside. If we want dx go outside, then the first thing you need to do, project this region D on the x-axis. So that means you find your smallest x coordinates and the largest x coordinates for all the points inside of D. So say from A to B. Now, then you go back to see what is the restriction for y to make this point inside of this region D. Okay. So this time it's not like, see your y is, for example, is here. It's not always bigger than C and less than D. It's from this point to that point. Okay, I mean this So it's not C and D. In fact, for giving different x, restriction for y will be different. Okay. So in this case, we just need to find what is this point and what is that point. To find that out, we need to know this curve, right? This curve, the bottom, you have bottom curve here. The bottom curve is y equal to, say, h1 of x. Then you have a top curve here. This top curve, say, y equal to h2 of x. So, for giving any x between a and b, then for all those points inside, right? All those points there is y is bigger than h1 of x and smaller than this point, which is h2 of x. When your x running from all the a to b, and you got all the points. Okay, so for the region is now rectangle, we can do this. Similarly, your region can be like, for example, like this. You can go y go outside, just like rectangular case. Dx dy. If you chose this order, that means, okay, remember outside those two things, they got to be constant, okay, because double integral give you a number. Okay, so this is our region D. If you dy go outside, first thing you need to do is make a projection of this region on the y-axis. So this will be your all the point here. The smallest y-axis will be this point, we call it C, and the largest y-axis for all the point inside will be less than D. Okay. So you put C here, D here. Okay. Everything in this strip. Anything in this strip, they have their y coordinates between C and D. Okay. So for the point to be in this region D, we have a restriction for x. Obviously, for giving y, your x, for all the x inside, they have to be bigger than this point, less than this point. Okay. So how do you find that point? You have to know this bottom curve. Okay, this is bottom curve. This bottom curve, say, is x is a function of y. We say g1 of y, and bigger than this bottom curve and smaller than this top curve. That's x is a function of y. Okay. So first of all the points inside of region D, their y coordinates bigger than C, less than D. For giving any y between C and D, your x must be bigger than this point and less than that point. That's G's 1 of y to G's 2 of y. Okay, again, you got two iterated integrals. Sometimes one is easier to integrate than the other. Okay. Now let's look at the example. Okay, we want to find a solid. We want to find a solid lies under this surface, z equal to x squared plus y squared. And above the region D here, my region D there is on the xy plane bounded by line y equal to 2x and parabola y equal to x squared. x and y. Think about z is above the board, okay, above this my plane. Okay, y equal to 2x. Y equal to x is a line like this, and y equal to x squared is a parabola like this. Okay. Our region D is the region bounded by those two curves. Y equal to 2x. This one is y equal to x squared. Okay, what do we want to find? We want to find, think about that. You have a surface above this region D, okay? We want to find the volume under this surface and restricted on the region D. So the volume can be found by double integral. fxy dA. Okay. What is my fxy here? My fxy is x squared plus y squared dA. Okay. How do we find this integral? We have to write as iterated integral. Now let's do it in two ways. Okay. Say like dy go inside, dx go outside. Okay. So the outside layer of integral is for x. Remember, it's always outside one. Those two is always a constant. So the first thing you need to do, make a projection of this region D on the x-axis. In other words, find the smallest x for all the points inside. Find the smallest x coordinates and the largest one here. Okay. So obviously this one is 0, right? Okay, how do we find these coordinates? So first of all, we have to find what? Intersection of those two curves. How do you find the intersection of these two curves? What do we mean intersection? That means, for example, this point satisfy both equations. So you set, okay, we have y equal to 2x and y equal to x squared. On the intersection of x and y equal, right? So you set y equal, you got x squared equal to 2x. Solve this one, x minus 2x equal to 0. You pull the x out. So you got x minus 2 equal to 0. Okay, you got a 2 solution for that. One is x equal to 0, one is x equal to 2. So x equal to 0, you got this one. And x equal to 2, that's what a 2 is. Okay, so this point, x is 2, what is y? X equal to 2, you can use either this one to find the y or this one to find the y. You got the same thing. Okay. So x equal to 2, y is 4. Okay. So since our dx go outside, find the restriction for x. We know all the points inside of a d that x is bigger than 0, less than 2. Okay, now let's see what is the restriction for y. You just fix x arbitrarily in between, between 0 and 2. See all the points here in region D, right? All the points there, the y coordinates is bigger than, for given x, is bigger than this point, less than that point. For given x, this is on the curve y equal to x squared, right? So you can find that number by x squared. Then your y is bigger than x squared, less than that number. That number is on the y equal to 2x, so you have 2x here. Okay, now we can integrate this. So what you need to do is integrate inside one. Okay, so inside the integral is about y. You treat x as a constant. So you integrate x squared, you got x squared y, right? Just think about 2. It give you 2y. X squared y. Then plus 1/3 y to the third. This whole sense evaluate at x squared and 2x. Then dx. Okay, 0 to 2. Now here you got to be careful. Okay, we're going to replace something by 2x, subtract something replaced by x squared. So we got x and y here. Which one we should replace by 2x? Since this is integral about y, okay, therefore whenever you see y, you replace it by 2x, then plus 1/3, you got y there replaced by 2x, so you got 2x to the third. Then subtract, same thing, replace y by x squared. So you got x squared replace y by x squared times another x squared plus whenever you see y replaced by x squared. So you got x squared to the third. Okay. This whole thing's integral about x. Okay, you simplify that, you got 2x to the third plus 8 over 3 x to the third minus x to the fourth minus 1/3 x to the sixth dx. Okay, once you integrate that, you know how to integrate this. This is a polynomial. Okay, this is simple integral. 216 over 35. So what is this number? That's the volume under that surface and restrict on the region D. Okay, let's find this volume again by, let's do that again by write with change the order. This time we go, y go outside, okay. dx dy. Okay, let's go back to that picture. So y go outside. So first thing is find out for all the points in the D, find smallest y coordinate and the largest y coordinate. We have so many points. Okay, so just make projection on the y-axis of this region D. Obviously, your y is what? For all the points in the D, the largest possible coordinate y is what? 4, right? And the smallest one is 0. So you put 0, y is bigger than 0 and less than 4. Okay. Then you look at what is the restriction for x, such that those points in the region D. Okay. Obviously, for giving y this time, for giving y between 0 and 4, your x is bigger than this point and less than that point. Okay, bigger than this bottom curve. Okay, what is that bottom curve? Bottom curve is y equal to 2x. This time you have to solve it. So your x is equal to 1/2 y. Because we're giving y, we want to find the x. Okay, bigger than, for giving y, your x should be this point, this length. This length is 1/2 y. Okay, so your x should be bigger than this point, less than this point. What is that point? On the top curve, for giving y, your x there is square roots of y. Okay, we take a positive one because this x is a positive. Okay, so see this length is 1 over square root of y. Okay, this is x. Okay, so here your x is bigger than 1/2 y and less than square root of y. Okay, now let's integrate that. 0 to 4. Now I can go ahead directly to do that because this is integral easy to integrate it. This time we'll integrate about x. So you treat y as a constant. First you got 1/3 x to the third. Second, y squared is a constant. So you got y squared x. Evaluated 1/2 y and square root of y. Then dy. Okay, this time you replace your, this is integral about x, so you replace x by square root of y, so you got 1/3 square root of y to the third plus y squared, replace x by square root of y, then subtract 1/3, replace x here by 1/2 y, 1/2 y, then this is the x to the third, plus y squared times x. X is 1/2 y, okay, dy. You simplify this. I'm not going to integrate it. This is a polynomial. Okay, you integrate that would give you the same answer if you do everything right. Over 35. Okay, now let me give you another example. This example we want to integrate double integral d. Function we try to integrate is xy dA. Okay, d here is a region bounded by a line y equal to x minus 1. Another is a parabola y squared equal to 2x plus 6. First, let's see what our d looks like, x and y. D here is a parabola. One is a parabola, like that. Another one is a line. This line is y equal to x minus 1. Just like y equal to x. Move down 1 unit. Okay. And this one is that parabola. Okay. Now, this region is our D, this shaded region. Okay. Now, before we do anything, we'll have to find these interceptions to describe this region. Okay. How do we find interception? Now let's set x equal this time. Okay. So from here, my x equal to y plus 1, right? So I put back here, I got a y squared equal to 2 times y plus 1 plus 6. I replace x by y plus 1. Let's give you 2y plus 2 plus 6 give you 8. Okay. So you got a y squared minus 2y minus 8 equal to 0, okay, which is y minus 4 y plus 2, right? So you got y equal to 4 and y equal to minus 2. Okay, so this point here, the coordinate y is minus 2. Then you go ahead, find x. Y is minus 2, so your x is minus 1. And at this point, y is 4, so your x is 4 plus 1 is 5. Okay, now we want to integrate this double integral over this shaded region D. Now we can, again, we can calculate this double integral by two ways. One is project on the x-axis, that means dx go outside, or project on the y-axis, then dy go outside. Now, obviously, for this problem, project on the y-axis is easier. Okay. Now, let's do that first. Okay, so we want to calculate this double integral d here. We decide dx go inside, dy go outside. Okay. So, if you do that way, project this region D on the y-axis, like that. So for every point here, find smallest y coordinate. You have so many points. Find the smallest possible y, which is what? Look at here, -2, right? Your largest y here for all the points in the D is 4. Okay, so it's 0 to 4. Then you fix y in between, arbitrarily, between 0 and 4. For given y, all those points inside, right? So your x must be bigger than this point, less than this point. This one is your bottom curve, this is your top curve. Okay. So for given y, how do you find that point? That point is on this curve. This curve is y squared equal to 2x plus 6. So I give you y, you just find x. So this curve, for given y, you solve for x. So x is equal to y squared minus 6 over 2. Right? Okay, that's your bottom curve. This is the bottom curve, which is y squared minus 6 over 2. Because we know the y, we want to find the x. This distance is our x. Okay, your x bigger than this number and less than that number. Okay, what is that number? That number is, for given y, you find x. So x is y plus 1. Okay. So top curve is y plus 1. Okay. Now integrate this. Okay, inside integral is about x. Treat y as a constant. So you got 1/2 yx squared. Evaluate at y squared minus 6 over 2 and y plus 1 dy. Okay, whenever you see x, this is integral about x. Whenever you see x replaced by y plus 1, so you got y plus 1 squared. Then minus 1/2 y replace x by this. So you got y squared minus 6 over 2 whole thing squared. Then dy. Again, this is a polynomial. Okay, it's easy to integrate it. I'm not going to do that. Okay, I just write down the number. It's 36. So 36 give you the value for that double integral. Okay, now how about we want to do this again. This time we want to x outside. Dy dx, we want to in this order. How should we do that? Now let's look at this shape D. Okay, what is our bottom curve? Your bottom curve is here and here. Okay, your bottom curve really is formed by different functions. This part is a parabola, and this part is a line. Okay, so you really cannot write as one expression. Therefore, you have to break your integral. Let me draw this one again. Okay. See, this time your bottom curve, x and y here. Your bottom curve is here and that. So, what we're going to do is break our region D to two regions. We call this D1, and this one is our D2. Okay. So your double integral D. Think about that. You have like a volume above this region D. To find the whole volume is like find the volume on the restricted on D1 and find the volume on restricted on D2. Add them together would give you the whole thing. Right? This makes sense. Okay. Now let's look at the D1. Okay, this is my D1. Remember, this time we want x go outside, y go inside. X. Okay, so look at this D1. Make a projection on the x-axis. So your x will be bigger than, what is this? This point is a -3. Okay, it's easy to find. And remember, this point we find out is what? -1. Here is -1. This is -3. For all the points in the D1, your x will be bigger than -3 and less than -1. Okay, so like that. Bigger than -3, less than -1. Okay, then fix x in between. See what's the restriction for your y. Okay, your y is obviously bigger than this bottom curve, less than the top curve. So let's find out what is those bottom curve and the top curve. Our curve here, what is our curve? Y squared equal to 2x plus 6. Okay, this curve is y squared equal to 2x plus 6. Okay, this whole thing, this parabola have two parts. If you solve the y equal to positive, negative, square roots 2x plus 6. Okay. If you take the positive sign, they give you top half. Okay, top half is take a positive sign because y is a positive. The bottom half here, bottom half, take y equal to negative square roots 2x plus y. Okay. Therefore, your bottom curve is a negative square roots 2x plus 6. Your top curve is positive square roots 2x plus 6. Okay. Now you integrate that, you will find the value for this double integral. Okay, I'm not going to do that. I just want to show you how do we find those four limits for the double integral. Okay, now let's look at the D2. Okay. dy dx. Okay, project D2 on the x-axis. Find possible smallest x coordinates for all the points. Obviously, your smallest x possible is here, right? Which is -1. I mean, -1 here is bigger than, it's less than this point, which is 5. Okay, we'll find out before. So 1 to 5. Okay, now you fix x in between, anywhere, doesn't matter. Okay, doesn't matter. Your bottom curve is always what? This line. Okay. This line is y equal to x minus 1, right? For given x, you find this point is x minus 1 and less than that point. That point is a curve y equal to square roots positive, okay, 2x plus 6. I'm not going to integrate this, okay? You integrate it and add those together, you're supposed to get the same number. For this problem, obviously, the first one is easier to integrate. Okay, now let's see one more example. This example is different than the previous two. Okay, we want to evaluate iterated integral this time. Before, they always give you double integral. They want you to calculate that. So you have to write as iterated integral. Sine y squared dy. Okay, for this problem, we cannot go ahead and integrate this because we're not able to find the antiderivative for this. Okay, next time you see sine y squared, don't try to integrate it. You are not going to find its antiderivative in closed form. Okay. Therefore, what we can do, as we know, this iterated integral can be written as double integral of some double integral over region D. Okay, so and we know this double integral can be written as a different order, same function, okay, just order different, dx dy. Okay, we don't know what are those four things here. Okay, we just say this iterated integral can be written as some double integral, and this double integral can be written as another iterated integral. Hopefully, this one is easier to integrate it, then we solve the problem. Okay. So before we integrate this integral, we have to figure out what is region D here. Okay. Before, we always know D, then we fix those four things. This time we know this four things. We want to figure out what is the D. Okay. Okay, now look at it here. Okay, x go outside. That means your x is between 0 and 1. Say here's a 1. Everything in this strip, their point x coordinate is between 0 and 1. So now let's see what's the restriction for y. Okay, now they said that y is bigger than x. You really read this? Remember here, x to 1. Those are bottom curve, top curve. So what is the bottom curve? Y equal to x is your bottom curve. Top curve is y equal to 1. So get those two things. Y equal to x. This is y equal to x. Okay. Top curve, see, you see 1. This is not a number. This is a function. Y equal to 1. So this is the curve y equal to 1. Okay, now they told us, okay, x is between 0 and 1. Everything in this long strip is fine. However, the y for giving x, y is bigger than this point, less than 1. So it's clear. This triangle is our region D. Therefore, this iterated integral can be written like this. Sine, that's what we want to evaluate, is equal to a double integral d sine y squared dA. And now we know what is d is. Okay, so Since we know the d, we can write this one as another iterated integral. This time we want to dx go inside, dy go outside. Okay. How do we do that? Remember, first things, look at all the points here. Find the smallest possible y and the largest y for all the points in the d. Obviously, y is this smallest y coordinate, right? This is the largest y for all the points inside this region. So it's 0 to what? 1. Then, for this region, see what is the bottom curve? This is your bottom curve. This is your top curve. So think about a fixed y here. Okay. Your x is what? Bigger than here, less than there. Okay. What is this equation for this y-axis? X equal to 0, right? X is, see, for any y, the x is always bigger than 0. Less than that. For given y, this sense is your x. Okay, so your x equal to y. For given y, you just say solve for x. So x equal to y. So you put y here. Okay, so those two iterated integral, both related with this double integral, so they're equal. And however, the second one is easier to integrate it. The first one is impossible. Okay, how do we integrate this? Now dx go outside. That means we have what? You treat y as a constant. So this integral gives you sine y square x, evaluate 0 and y, dy. And this one equal to, when you see x replaced by y, okay? So you got y, subtract, replace x by 0, which is 0. I'm not going to write it like this. Okay, this one is easier to integrate, obviously, yes. So you just need variable substitution. Let u equal to y squared. Then your du equal to 2y dy. Then this integral give you sine u. Okay, sine u. Then y dy. Y dy give you 1/2 du. Okay, there's two things you can do. One is you keep 0 and 1, okay? But once after you integrate it, you change u back to y, okay? So this gives you 1/2 cosine u negative. Give you negative, okay? Either you change it here, you don't change it here, okay? Let me now change that. I change it u back, okay? What's your u? Y squared. Okay, now you evaluate 0 and 1. So you put 1 there, give you minus 1/2 cosine 1. The minus replace y by 0. Cosine 0 give you that. Okay.